All right, everyone, welcome. Today, we're going to get into a really fundamental concept in power electronics. We're talking about how to safely handle the energy that gets stored up in an inductor, especially when you try to turn it off. This is a classic problem for engineers, and understanding the solutions, well, it's absolutely essential if you want to design circuits that don't, blow up.
So here's our game plan for today. We're going to follow a path that you'll see over and over in engineering. First, we'll identify a really dangerous problem. Then, we'll introduce a simple, elegant solution. And finally, we're going to see how we can make that solution even better but improving its efficiency. Okay, let's dive right in. We're starting with the problem, a really critical and honestly destructive issue that can happen in tons of common switching circuits that have an inductive load, like a motor or a solenoid. So I want you to picture this. You've got a super simple circuit, a power source, a switch, and an inductor. The switch is closed. Current is flowing happily through the inductor. Now, what do you think happens in the exact moment we flip that switch open and break the circuit? The answer? Well, it's something pretty nasty, a massive voltage spike. The inductor is going to generate a crazy high voltage right across those opening switch contacts, all because it's trying desperately to keep that current flowing. So, what's the physics behind this? It's a core principle you have got to remember. Inductors store energy in a magnetic field, and their whole identity, their whole reason for being, is to oppose any change in current. So when you try to slam that current to zero instantly, that dIdt term, the rate of change of current, becomes gigantic. And since V equals L times dIdt, the voltage becomes gigantic too. And all that energy, it can't just disappear into thin air, right? It has to go somewhere. So it literally jumps across the air gap in the switch as a visible, super hot spark or an arc. And this isn't just a pretty light show. It's a destructive force that will eat away at the switch contacts and can easily fry other sensitive components in your circuit. So that's the scary part. How do we fix it? How do we tame this beast? Well, thankfully, engineers came up with a really elegant and incredibly simple solution that you will now see everywhere in power electronics. And here it is. The solution is just adding this one little component, the freewheeling diode, which is labeled DM right here in the diagram. Now, pay close attention to where it's placed. It's in parallel with our inductive load. And look at its orientation. The arrow is pointed against the normal direction of current from the source. And this really gets to the heart of it, and I'm quoting our text here. A path must be provided for the current in the inductive load. That's the whole idea. The inductor's going to make that current flow, one way or another. So we give it a safe low voltage path to follow, instead of letting it create a destructive high voltage path through the air. Okay, to really get how this little diode works its magic, we need to do what engineers always do. Break the circuit's operation down into its different states. We'll look at two distinct modes. Mode 1, when the switch is closed, and Mode 2, when the switch is open. And this diagram from the book just lays it out perfectly. On the left, you've got Mode 1, switch closed, business as usual. And then on the right, in Mode 2, the switch is open, and you can see how the current path completely changes. The diode suddenly becomes the star of the show. All right, let's really break this down. In Mode 1, the switch is closed. Current is flowing from our source through the inductor, and energy is getting stored in its magnetic field. Now, because of the voltage from the supply, our diode, DM, is reverse biased. It's basically an open circuit, just sitting there doing nothing. But the instant we open that switch, the inductor's magnetic field collapses. The voltage across it flips polarity, and that immediately forward biases the diode. Now we're in Mode 2. The main switch is totally out of the picture, and the current just freewheels in a nice, safe little loop through the diode and the load. Now this is where it gets really cool. These waveforms show us exactly what's happening to the inductor current over time. See that period labeled T1? That's when the switch is closed. The current ramps up exponentially as the inductor charges up. Then, right at the end of T1, the switch opens. But look, the current doesn't just crash to zero. No way. Instead, during the T2 period, it decays away nice and smoothly, exponentially, as it circulates through that diode loop. That's our stored energy being released safely. Okay, great. So we've solved the safety problem. The switch is protected, our circuit isn't going to arc and spark. Fantastic. But, in power electronics, safety is just one part of the puzzle. There's another huge consideration we always have to think about: efficiency. So yeah, the freewheeling diode is a perfect fix for protecting our components, and for little, low-power circuits, it's often all you'll ever need. But when we start talking about efficiency, it's got a pretty big downside. So I want you to really think about this for a second. That freewheeling current we saw in mode 2, just circulating around and around in that loop. We said the energy is dissipated. But what does that actually mean? Where is that energy going? Well, here's the catch. All that energy that you so carefully pulled from the power supply and stored in the inductor's magnetic fields, it just gets turned into heat. It warms up the diode and the resistance of the load. It's just lost, gone forever as wasted power. And if you're designing a high-power system or something that runs on a battery where every last bit of energy counts, this is just not acceptable. So that brings us to the next logical step, right? A more advanced solution. How can we not only protect the circuit, but actually recycle that trapped energy instead of just letting it burn off as useless heat? And this circuit here shows us the next evolution. You'll notice a couple of key changes. First, we've added a second winding, which basically turns our inductor into a transformer. And second, we've moved and reconfigured the diode. Now we call it a feedback or an energy recovery diode. The entire goal now is to take that stored energy and push it right back to the power source. And just like before, the best way to understand this is to look at it in two modes. In mode 1, the switch is closed. Energy gets stored in the transformer's magnetizing inductance, just like before. But check out what happens in mode 2. When the switch opens, that collapsing magnetic field induces a voltage in the secondary winding. This forward biases our diode, D1, and it literally pumps current back into the power supply. We're recycling. And the waveforms, again, they just prove it out beautifully. During T1, you see the primary current, I1, ramping up nice and linearly, storing energy. The moment the switch opens, I1 drops to 0. But look at the second waveform. During T2, a new current, I2, appears. That's the current in the secondary winding, and that is the very picture of energy being returned to the source. It's not being wasted as heat anymore.
And of course, being engineers, we don't just want to say it works. We want to quantify it. We want to put numbers to it. By following these steps from the example in our text, we can use all the circuit parameters to calculate precisely how much energy gets recovered and sent back to the supply in every single switching cycle.
Okay, so let's boil all this down. Let's wrap up. What are the key principles, the big ideas, that you absolutely have to walk away with today? These are the things that should become second nature for you as a designer.
These are the big ones. First, and you can never ever forget this, you can't just leave an inductive current with nowhere to go when a switch opens. You need a plan. Second, the simple freewheeling diode is your first line of defense. It's the simple, safe path, but it just wastes the energy as heat. Third, for better efficiency, you have to think about energy recovery, using a transformer and a feedback diode to send that energy back to the supply. And all of it comes from that one fundamental truth. An inductor will fight to keep its current from changing. Getting these concepts down is absolutely fundamental for designing pretty much any power converter. So the question I'll leave you with is this: what other little imperfections in our circuits are we going to have to solve for next?